Work towards developing a quantitative EEG-based biomarker for SLC6A1. Oh, I'm also our CSO at SLC6A1 Connect. It's coming up on about 5 years now. Yeah. Oh, thank you, thank you. All right. So here we have some background information and prevalence points, and the primary focus here is that a strong understanding of these quantitative EEG properties is vital given the high rates of epilepsy seen among patients. Additionally, the overall focus here of the presentation will be that we know there are EEG improvements following treatment with Ravicti, and so being able to quantify these changes will be beneficial to a multitude of ongoing clinical trials in the community, as well as increasing our basic science knowledge. All right, so I'll start over here with a kind of conceptualization and review of what we're aiming to do. So initially we had a pediatric epilepsy expert, Dr. Zachary Grinspan, and he marked these delta bursts in 400 seconds of one pre-treatment EEG for use as a gold standard. And pre-treatment here refers to the fact that the patient had not received Ravicti, just emphasizing that clinical trial connection. Now, reports from this ongoing clinical trial suggest that these bursts decrease after treatment with glycerol phenylbutyrate, and the child was selected because they became seizure-free after treatment with the medication. And so in terms of selection of pipeline parameters, existing literature was reviewed extensively, although informally, meaning we didn't conduct a formal literature review, but we did develop a knowledge of parameters utilized for other variants or other mutations. And then our expert clinician also provided insight into EEG trends and related properties that he was seeing in waveforms that might be nice to investigate. And this led us ultimately to zone in on the fact that these seizure patterns often reflect increased amplitude, slow waves, and a sort of rhythmicity. And so Dr. Grinspan will often characterize these as bursts of rhythmic delta, sometimes with a notch and sometimes with a spike wave pattern. All right, so we'll dive in here first. So initially, we created this first pipeline to verify the selection of these parameters. So 3 spectral features were calculated at 1 second intervals. So we have 1 second of data for each at a time, and then we shift that down the EEG in different lags. So the first parameter is delta power, which in this pipeline is the total power from 2.5 to 4 hertz represented in microvolts squared, and that's in integral form. So that lends itself to the high figure that you see reflected below in the table. Then we moved on to autocorrelation, which is the closeness of the wave to itself, so moving down the same channel pair signal with these lag times. And then the third parameter we selected was spectral entropy, which is the distribution of power across the frequencies of interest that correlate to our seizure activity from about 1 to 30 hertz. And so you can see here in the table for this initial EEG we had for the patient, these were the trial and error determined thresholds that we decided would be investigated for these 3 parameters. All right, so you can see here the results for this first pipeline. So we had 25 bursts of seizure activity in this 400-second span. What you're seeing here in the plot, these green zones were areas that were identified as absolutely containing seizure activity by the reviewer, with yellow zones reflecting periods where there was potentially activity. These blue triangles are what we call hits, and so a hit is when all 3 thresholds determined in the last slide were met. And so that's your threshold for power, for autocorrelation, and for spectral entropy being met there. So you can see very promising statistics here, but of course, with only 400 seconds of data for one patient, we worry about overfitting and generalizability. So to sort of address those concerns, we moved into pipeline 2. And what this involved was a real focus on optimizing selection of the thresholds via exhaustive search maximizing. And what that means is that essentially you're running through one EEG for the patient to determine baseline threshold levels that will apply to further EEGs for that same individual. So this improves generalizability because it applies threshold logic, but for each patient separately. So we use this F1 metric sourced from the literature, which weights PPV and sensitivity to determine what these thresholds should be. Another key point here before moving into the results of pipeline 2 is that the delta power parameter was modified, so it's no longer in integral form. The amplitudes in the delta power range were squared to produce a vector, which we took the median of. All right, and so here you can see some preliminary results from this type of pipeline. And so the table reflects an example of thresholds that could be determined and in fact were determined for this patient based on one trial EEG. And so this would be something that would be separate for each individual rather than sort of being blanketed across. What you can also see reflected here is that prior to treatment with Ravicti, there's a higher percentage of seconds exceeding the 3-part threshold, so a higher percentage of seconds reflecting seizure activity. And we can see that this decreases post-treatment. These predictions were made with the algorithm before knowing whether these EEGs were pre or post-treatment, and then these predictions were verified by our expert reviewer. All right, so in thinking about generalizability and potentially other metrics to examine, we moved into a third pipeline where we looked at cross-correlation, which is the fit of the waveform across the 18 channel pairs in each second-long time span. And so autocorrelation was comparing the fit of the waveform to itself. This is looking across the multitude of channel pairs to get a better picture of how this seizure might be playing out. Across the EEG, 25th percentile, 50th percentile, and 75th percentile data was calculated for each 1-second interval. And so this led us to having 12 predictors because, again, we have these 3 percentile levels for our 4 variables, those being the initial 3, now with the addition of cross-correlation. We then implemented logistic regression models and determined the best subset, which essentially weights both the fit of the model and the simplicity to ensure that your model fit isn't only improving simply because you are adding more parameters. And so this led us to see the following results. And so in this same 400-second time span as was reflected in pipeline 1, what you're seeing here in the green zones are that the model is able to show an increased probability of seizure activity, which lends itself to increased generalizability, because if this applies across the board, then we would be able to not only determine thresholds for patients more separately, but also see that we don't even have to use necessarily exact thresholds, but can base this on increases relative to values using 75th percentile. Okay, and then finally for conclusions, so all in all, we have developed a measure to detect these SLC6A1 related EEG abnormalities and use this to discriminate pre-treatment from post-medication EEGs. Ongoing work will explore additional features, and we will continue to hone in on ways to improve generalizability across the full set of 10 patients from the ongoing glycerol phenylbutyrate clinical trial. Further properties such as wavelet forms can be used to simplify models as we move towards our ultimate goal of improving insights for, again, the multitude of ongoing clinical trials in the community. Thank you.